Hello and welcome to this session in physics. In this session, we'll be looking at Introduction to Physics. Under Introduction to Physics, we'll be looking at the meaning of physics, and I'm going to give you 3 precise definitions of physics. The first is that physics is the scientific study of matter and the study of energy and how these two phenomena interact with each other. We have different forms of energy. We have energy in the form of motion, we have energy in the form of light, energy in the form of electricity, energy in the form of radiation, energy in the form of gravity, and so on and so forth. The second definition is that physics can also be defined as a natural science that involves the study of matter. Of course, we know that matter is anything that has mass or weight and occupies space. Now, it involves the study of this matter and how this matter moves through space-time, as well as applicable concepts where this phenomena can be applied, such as in the study and force. And then more broadly, the third definition is that physics is the general analysis of nature, which is conducted in order to help us better understand how the universe behaves. So these are the 3 precise definitions of physics. Now, as you can see from the slide here, you would notice that physics is divided into 2 main branches. They are classical physics and modern physics. These are the 2 main branches that physics is divided into. And now let's take the definition of classical. Classical physics consists of the following. Things like mechanics, heat, optics. Of course, you know, optics has to do with light waves and other things associated with sight. And then we have wave and sound, we have electricity, we have magnetism. All these phenomena are classical physics. And then what about modern physics? This aspect of physics covers the aspects of energy, matter, and how they relate with their atomic and subatomic levels. Of course, you know that an atom is the smallest indivisible particle of an element. So, modern physics helps us with atomic and subatomic levels of matter energy. There are also some other fields of physics. These fields are geophysics, astrophysics, biophysics, nuclear physics, and engineering physics. Now let's look at the importance of physics. The importance of physics cannot be overemphasized. Physics has developed so many things that we use today. Things such as television, such as computer. We have domestic appliances, such as our pressing iron. We have our electric kettles. We have our electric stoves, and so many other things we use domestically. The light bulb too is an example of what physics has helped to invent. And then in bioweapons, we have nuclear that have been developed using the study of physics. Another importance of physics is in the field of thermodynamics. In the field of thermodynamics, advances in physics has helped to the development of motorized transport. And then a final importance of physics is in the development of mechanics, the advances in mechanics. This has helped to inspire the development of a branch of mathematics we call calculus. And we have the differential calculus, and we have integral calculus. Calculus is a branch of mathematics that helps us to see how one quantity changes with respect to the other. And its importance too in the field of engineering cannot be overemphasized. At this point, I want us to look at quantities and units. In physics, measurements play a very important role. There is no law that has been made, no principle that has been defined, no quantity meaning unless it can be measured. And for that reason, measurements play an important role in physics. A unit has to be defined before any kind of measurement can be done. Let's say your mom asks you to go and buy rice. You don't just go to the shop and tell them you want to buy rice. Of course, you have to know the quantity of rice you want to buy. So, you have to tell them, I want to buy 2 cups of rice. You see that cup is a unit of measuring rice. or you're asked to go to the filling station to buy fuel, you don't just go there and tell them that you just want to buy fuel. You have to tell them the quantity, and that's where you tell them, I want to buy like, okay, 2 liters of fuel. Or somebody asks you, how tall are you? You don't just tell the person, I am 5. 5 what? Is it $5 tall? Is it 5 years tall? Or is it 5 meters tall? And that is what it's supposed to understand. Units help us to identify and give meanings to quantities. And so, different systems of units have been used in the past. These systems include things like the foot-pound second system, used predominantly in Britain. And then we have the centimeter-gram system, known as the CGS system. And then we have the meter-kilogram second system, known as the MKS system. But today, the system that has gained universal acceptance is usually called the SI System International. System International units of measurement. So that is the one that has gained international acceptance today. On your slide here, you can see some measuring instruments we use today. Things like the vernier caliper. We have things like the micrometer screw gauge. We have things like the spring balance. We have our voltmeter. We have our beam balance. We're going to look at some of these instruments at one point or the other in this video. At this point, let's talk about physical quantities and their units. You see, physical quantities are often divided into fundamental quantities and derived quantities. Fundamental quantities and derived quantities. Units, respectively, are divided into fundamental units and derived units as well. So what do we mean when we say fundamental quantities? Well, fundamental quantities are those basic quantities. The key word here is basic. They are the primary quantities. They are independent of others. They exist alone, and they do not rely on other quantities to define them. They are the basic quantities. They are the upon which most quantities depend for their derivation. Similarly too, fundamental units are the basic units. They are the primary units. They are the foundation units upon which other units depend for their derivation. It is a combination of fundamental units that give us what we call derived units. The same thing applies to derived quantities. We have 3 most basic quantities in physics. As you can see from the slide here, they are length, mass, and time, respectively. Now let's look at the table of some fundamental quantities and units that we have in physics. The first one you can see here is length. Length is measured in meters. So we say length is the quantity, the unit is meter. And as an abbreviation, it's just written as m. So when you say like 2m, 2m means 2 meters. And then the second one we have here is time. Time is measured in seconds, and the short form is written as, when I say 5s, I mean 5 seconds. And then the same principle applies to mass. Mass is measured in kilogram, written as kg. So when you see somebody writing 10 kg, it simply means 10 kilograms. And then we have electric current. Electric current is measured in ampere. And ampere is written in short form as, if I'm to write 12A, it means 12 amperes or 12 amps. And then we have temperature. Temperature is measured in Kelvin. Kelvin is written shortly as K. And then we have amount of substance, which helps us to quantify the amount of elements, atoms, molecules that make up a particular compound, and it is measured in mole, written as a short form of MOL. And then we have the last one, luminous intensity, which is measured in candela, written as CD. Now, when you look at these units and quantities very well, you notice, for instance, the SI unit of length is meter. It does not mean that we cannot measure length in centimeters or cm, like we cannot measure length in cm. Of course we can measure length in cm. When it comes to time, it does not mean we cannot measure time in hours or days or years. When it comes to kilogram, it does not mean we cannot measure in decigram, and so on and so forth. When it comes to current, we can also measure in milliamperes. But why are these ones chosen? They are chosen because, like I said earlier, they are the SI, System International Units of Measuring units and quantities. At this point, let's look at derived quantities, and as the name implies, derived means gotten from something. And so we say derived quantities are units, are those quantities and units that have been obtained by simple combination of fundamental units and quantities. By simple combination, think of it as your father and your mother. When your father and your mother came together, they gave birth to something, and that product was you being their child. So the fundamental units and quantities, they are like the parents, they are the foundation, and then the children, the products, what they produce are what we call units and quantities. So fundamentals combine to give us derived units and quantities. The following on your slide here is the derived quantities and units we have in physics. The first one is area. Area is given by a product of length and breadth. So length times breadth simply gives us, since length is measured in meters and breadth is also measured in meters, that gives us meter squared. M times M, M squared. The same applies to volume. Volume is measured in length, breadth, and height. Length is measured in meters, breadth is measured in height is measured in meters. M times M times M gives us meter cubed. Density also. Density is gotten from the ratio of mass to volume. So when mass divides volume, we're going to have density. Of course, we know mass is measured in kilogram and volume is measured in meter cube already, and that gives kilogram per meter cube. In velocity, velocity is gotten from a ratio of displacement to time. Displacement divided by time. Displacement, that's time is measured in seconds, and that gives us meter per second. Acceleration is given by a change in velocity to time. Change in velocity to time gives us meter per second squared. And then finally we have force, which is gotten from a product of mass and acceleration, and that's why popularly we have F-M-E, force equal to mass times acceleration. The SI unit for force is Newton. Alternatively, we know that mass is measured in kilogram, and acceleration, like we said before, acceleration is measured in meter per second squared. So it's more like merging two of them together, like saying kilogram times meter per second squared, and we're going to have kilogram meter per second squared. This is another way of writing the SI unit of, don't want to use Newton. We have countless other derived units and quantities, and I'll urge you to take a look at the notes attached to this video to get a greater look at them as well. Now let's look at the differences between fundamental and derived units. The differences are that 1. Fundamental units are the standard units of measurement. On the other hand, derived are not the standard units of measurement. They are gotten from fundamental. Fundamental is generally accepted all over the world. It means whatever unit of measurement we use in Gambia will also be used in US, respectively. It is generally accepted all over the world. But derived units are not accepted. For example, Gambia has their own currency of buying and selling. US has their own currency, and the two currencies are not the same. So you cannot use Gambian currency to go to US and pay for a good or commodity. And then the third difference is that fundamental units also form the basis of measurement. They are the basis of measurement, whereas derived units are not the basis of measurement. They are simply standing on something. By international organizations, fundamental units are accepted by international organizations. But when it comes to derived units, though they are accepted internationally, they were formulated by individuals. They were not brought about by a consensus of different persons together. They were formulated by single individuals. Derived units are known units, but fundamental units are SI units. That is, they are an international system. And then let's look at the differences between fundamental quantities and derived quantities. Fundamental quantities, just like in fundamental units, they are generally accepted. They are just accepted, the basis of something. And then the second one is that they are based on an international system. That is for fundamental quantities. But fundamental units are formulated. They are gotten from the fundamental quantities. the derived quantities are gotten from fundamental quantities. Fundamental quantities are unique for their ability to stand alone, whereas derived quantities cannot stand alone. They need help for them to have meaning. Fundamental quantities have direct calculations, but for derived units and quantities, their calculations are derived. And the last one is that fundamental quantities are basic units of measurement, but derived quantities and units are not basic units. At this point, let's look at dimensions of physical quantities. From your slide here, you'll see that the dimension of a physical quantity is the way it is related to the quantities of mass, length, and time, respectively. So, mass is measured in kilogram, but mass is written as capital letter M. Length also is measured in meters, but it is written as capital letter. And then time is measured in seconds, but time, T, is written as capital letter T. So that gives us an MLT system, mass, length, time. Those are dimensions of these three physical quantities. Level of few important physical quantities and their dimensions. For instance, velocity. Velocity, like we said in the previous slide, is a ratio of displacement to time. In other words, displacement over time gives us velocity. Displacement is measured in meters, time is measured in seconds. That gives us meter per second. And of course, you know that displacement is all about length. Second is all about time. So that gives us LT raised to the power minus 1, length per time. And that's what you see here on the slide. Acceleration to meter per second squared, just like saying length over time squared. And that gives us length per time squared. And that's what you have in second information here. And then for force, like I told you, force is kilogram meter per second squared. But we both know that kilogram is measured in mass and mass, M, and then meter is length, and then S, which is the second, is time. And then all you just have to do is put the negative index there, minus 2. So mass, length per time squared. The same applies to momentum, which is mass, length per time. Density, kilogram per meter cube, which is mass, length, cube. And then pressure, which is Newton per meter squared. Then we have mass per length per time squared. So this is some important physical quantities and their dimensions. Thank you for joining us in this lesson. To refresh your memory on what we just discussed, please take the tests that will appear on your screen.